science enthusiasts. My name is Jason Zakowski. I'm a high school chemistry teacher and science communicator, but I'm also the dog dad of Bunsen and Beaker, the science dogs on social media. If you love science and you love pets, you've come to the right place. So put on your safety glasses, do up your lab coat, hold on to your tail. It's time for the Science Pawdcast. Hello, everybody. Welcome back to the Science Pawdcast. We hope you're happy and healthy out there. If I could be real at the start of the Science Pawdcast, I just want to say that our family's hearts are going out to the people of Ukraine. Chris's mom's side of the family is Ukrainian, and they have ties to Ukraine, and it's just heartbreaking what's happening. There's not much currently that we can do aside from donating to places like Red Cross in Canada. The government's matching donations, so we're doing that. And also, we've switched out the prizes of our pet chat spaces. We have prizes that people win in the little game. And instead of prizes, we are donating to the Red Cross in the winners' names. It's something we can do. I don't know, maybe makes me feel a little better. And if you know somebody in Ukraine or you're a listener from that area of the world, just know that we are thinking of you. On the Science Pawdcast this week, we have a type of bacteria with chainmail. What? And in pet science, we've got yet another study that shows that animals boost your brain power. It's a little bit of confirmation bias, but the science is just stacking up about the benefits of our furry friends. In the Ask an Expert section, we have Dr. Iain Bancarz, who's a computational biologist, but's crunching the numbers on cancer. Hey dogs, a son was talking to his dad, and he said, "Hey dad, did you know that corks come from trees?" And the dad said, "No, son. Quarks come from particle accelerators." Hey-o! Okay, that's a good one. All right, on with the show, because there's no time like science time. This week in science news. So if you know who I am as a person, if you've been listening to the podcast a bit, you know I'm a nerd at heart. And I build these amazing, they're getting to be amazing, not to toot my own horn, but they're getting better and better, these costumes that are based on movies and video games. And I am fascinated with armor and weapons. And when I saw bacteria has chainmail, I was like, oh man, we are breaking down this news story, this science story on the Science Pawdcast. The bacteria we're going to be talking about with the quote-unquote chainmail is the one that makes your gut all roily and goily and uncomfortable. And it's from taking basically antibiotics for something else, and then this not-so-great gut bacteria takes over. It's called C. difficile. Your normal microflora keeps it in check, but as antibiotics kill everything else, this type of bacteria is notoriously resistant to antibiotics. And in the United States, if we're talking American data, a lot of people have infections from this. 500,000 people, 500,000 people a year. It makes it hard to treat for doctors when the best weapon that they have is something that the bacteria laughs at. I had heard about this C. difficile bacteria. I heard about it, and I knew that it was like something from is antibiotic resistant. Of course, I'm a chemistry person, so microbiology I don't really pay much attention to. But in this study, it breaks down why the bacteria is so resistant to antibiotics. It has to do with the shell of the bacteria. This was reported on February 25th in Nature Communications. Now, the barrier around this bacteria is known as the S shell. It basically, in a nutshell, it prevents stuff from breaking down the bacteria, either like from your body. Enzymes that might digest the bacteria or screw it up can't get through this S shell. The research team used fancy-dancy X-rays. The research team used fancy-dancy X-rays to take a peek inside the bacteria. And coupled with electron microscopy and a bunch of other people who knew what they were talking about, they made an image and then analyzed what the heck was going on with this shell. When they zoomed into the shell, they found tightly linked proteins with teeny tiny gaps, and it gave the impression of chain link armor. Now, I've worn real chain link armor a couple times in my life. Again, remember, I'm fascinated with armor and weapons. There's a group in Red Deer that are they're not LARPers. They're like actual medieval people that wear medieval stuff and they fight each other. It's actually growing in popularity. You're gonna want to Google this, I think, after. But it's like boxing or MMA, but you wear like medieval stuff and you just beat the tar out of each other. The chain link armor I wore, it was interconnected rings. It was wicked heavy. Adam tried a few tricks with it. Like the guy I borrowed it from because I was shooting something for a radio station, blah, blah, blah. And the guy said, yeah, it'll protect you from a knife attack. And Adam actually, this was when he was younger. I was like, Adam, you need to try and slash me with this knife. And he was like, I don't want to do it. But he eventually worked up the courage and he slashed me with the knife and I was completely unhurt because the chain link doesn't allow slash. You could maybe get poked through it, like with a really sharp sword or an arrow or something like that. Okay, I've taken our conversation off the rails. Let's get back to the bacteria. These small gaps are so small and so far and few between, very few molecules can actually get through them. And that includes antibiotics. Another reason why the analogy holds up is the outer S shell that looks like chainmail is flexible. So just like a shirt made of chainmail, you can move because the whole thing is fluid. Now, this may seem scary because you have little tiny microorganisms that are wearing armor. What's the next thing they're going to have is like swords and hammers and flaming arrows and stuff like that. Well, the good thing is that usually our science teams can outsmart whatever arms race there is with bacteria. And the team found that if they removed the S shell, it became really susceptible to a whole bunch of different enzymes. And the team found that a saliva enzyme called lysozyme just busted open this bacteria. Now, again, how are you going to get this enzyme directly to this bacteria? The team was pretty confident that specific drugs could be used to combat C. diff and really help out folks that are infected. In the study, it said that 1 in 6 people who are on some kind of like serious antibiotic treatment have a secondary infection from C. diff. That's a lot of folks that could benefit from this targeted treatment to remove the chainmail. I don't know. One of the things that the guy I borrowed the chainmail from is like, don't get it wet. It's like you're a gremlin or something like that. And it's oily. They have to keep it all oiled up all the time. I didn't know that because if you don't, it starts to rust. So getting rid of this bacteria shell may be just as simple as making somebody's chainmail wet. That's science news for this week. This week in pet science, it's always great when a scientific study links up with my confirmation bias that pets are amazing. I don't go looking for these studies, but they pop up on my feed. I have to talk about this one. So here's the Cole's notes. Here is the, what is it? The 5,000 foot pitch. Well, I don't know. I've been talking to marketers on Twitter Spaces sometimes, and they've got all these buzzwords. Here is the pitch. Having a long-term pet companion could or does delay memory loss and other kinds of cognitive decline. Great. So as humans age, our brain ages too. And it reaches a point where it doesn't get sharper. It gets a little duller. It starts to break down. There's a greater chance of things like Alzheimer's and cognitive disorders. It happens with dogs. It happens with humans. It happens with everything as it ages. Now, the study looked at pet ownership and the beneficial aspects of it with verbal memory. So like memorizing word lists in a research scenario. So it was pets and your ability to remember words. Sociological doctoral candidate Jennifer Applebaum from the National Institute of Health is the one that's the author of the study. And it's not just cats and dogs that can boost the brain. This is exciting for folks that have other pets. And they're always like, what about the rabbits? Well, let's see. People in this study cared for other types of animals, hamsters, reptiles, fish, and rabbits. But dogs were the most prevalent in the study. followed by what other animal do you think? That's right, cats. This study found correlational evidence with long-term pet ownership. So this is like having a pet for 5 years or more. That had the greatest benefit. And they had like this fairly complicated grading scale of cognitive decline over the 6 years the study went on. And they had a point system, and having pets for that long length of time decreased the decline by 1.2 points on this system. And that was compared against people who had no pets at all. So it suggests that long-term pet ownership has something to do with the delay or being protective against cognitive decline. Now, while the study could not make a determinative conclusion as to why it helped with cognitive decline, we can just look at what other studies have already said about owning a pet. 1, pet ownership, especially dogs, you get more exercise. 2, interactions with any kind of animal, mammals more than reptiles and fish and birds, decrease the stress hormone cortisol, which has a whole bunch of issues with stress, heart health, cardiovascular disease. If you have a lot of cortisol, chances are you're going to have problems from that a little bit faster, and that may correlate to stuff that's going on in your brain. 3, interactions with animals of any kind, if you like that animal, of course, decreases your blood pressure. And again, high blood pressure all of the time definitely has negative consequences on our entire organ systems, the brain being one of the biggest organs in our body. 4, having pets allows for more social interaction with people outside of our normal family, and that social interaction may stimulate the brain. 5, it's engaging for older folks that have pets who live alone, they've lost their spouse. That animal is constant mental enrichment of their environment. It's literally like giving Bunsen or Beaker a Kong. They're engaged in their activity. And for folks that maybe live by themselves or have especially during the pandemic, have limited interactions with other people, the animal could be their interaction, constantly stimulating their brain, working it out like a muscle. So while we can't conclude 100% why, the study showed that having a pet for more than 5 years had a good impact on slowing mental cognition decline. I love it. That's Pet Science for this week. Hey everybody, before we get to the interview section, I thought I would just give you some ideas about how you could support the Science Pawdcast. Number 1, you could support us on Patreon. Check out patreon.com/BunsonBurner. There's multiple tiers of support, and the lowest tier of support is not much more than a cup of coffee a month. The second way is you could check out our merch shop. We've worked really hard to partner with clothing companies that do a great job of providing vibrant colors and soft feels. We also have the Beaker Stuffy for sale. It's so cute. The third way you could support us is giving us great reviews on our podcast playing apps. Any kind of review helps. And if you can't find a review, share our podcast with people. Thanks, everybody. Now back to the interviews. It's time for Ask an Expert on the Science Pawdcast, and I am thrilled to have Dr. Iain Bancarz, who's a computational biologist, with me today. How are you doing today, Iain?
Very well, thank you.
Where are you calling into the podcast from? Where are you in the world?
I am calling from Toronto, Ontario, Canada, here in the big city.
Oh, you're out in Toronto, as they say sometimes.
I am. I'm in Toronto. I tell you, the time difference is really bad when I want to watch Edmonton Oilers games because I come from Edmonton originally.
Ooh, right. You had mentioned that you were born and raised in Edmonton, or just spent a bit of time here?
Pretty much born and raised. I moved away from Edmonton when I was 13, so my kind of formative years were there.
Oof, yeah. So you grew up with the Oilers, and any game that starts at 9, it's like 11 o'clock for you out there, hey?
Yeah, exactly. It's really tough.
Do you miss the River Valley, the Edmonton River Valley?
Yeah, it's pretty nice. I used to go there as a kid. I mean, Toronto has plenty of nice rivers and woods and things nearby. What I really miss is being able to get to the Rocky Mountains. Those were nice.
Oh, yeah, I take that for granted. I was talking to another guest. I was like, yeah, we're just going to go to the mountains for the weekend. And they're from Toronto. And they're like, So yeah, it's a bit of a drive/flight for you folks to get to the Rockies for sure.
Yeah, just a little.
So, Doc, let's talk about your background. You have a doctorate. You're a computational biologist. We like to know a little bit about like your educational journey. How did you get into science? What training do you have? What's a computational biologist? Those are really big questions, but our audience loves to know that kind of stuff.
Okay, yeah, happy to tell you. So, as I say, born and raised in Edmonton. When I was 13 years old, so my dad's Canadian, my mom's British, and my family moved to the UK. So I kind of completed my secondary and university education there. And I started off doing pure mathematics, just because I found it interesting, really. Not so much at school. At school, I was more into physics, but I got to university, and so I was doing like a course load that was heavy on theoretical physics, but also had me doing some pure math modules. And I found those really fascinating. So, because at school level, mathematics is more kind of, they give you the method, you turn the handle on the method, and the answer pops out the other end. At the university level, it was more about asking why things are true and proving them to be true, which I found really exciting. So I did that and completed my degree in it and tried to figure out what to do next. And there was funding going for a PhD in computational linguistics. And I did not know anything about that, but it sounded kind of cool. And, I'd enjoyed, being a student and learning things. So I wanted to keep doing that. So that's what I did. All of this, by the way, both undergrad and PhD, was at Edinburgh University in Scotland, which has a really good, not that I knew this when I signed on to it, but they have a very good center for computational linguistics and artificial intelligence more generally. So this was, basically applying computational methods to language and trying to understand it. So I started my PhD in 2001. So these methods were not as sophisticated as they are now, but it's kind of the roots of all the really clever voice recognition stuff and text recognition that we have today.
Oh, there you go. That I was wondering what that would lead into. Sorry, I cut you off. I just the light bulb just went on in my head. Light bulb.
Yeah, exactly. I mean, having done a PhD in the subject, it's easy to forget that these terms are not known to everyone. But yes, that is what it ties into. So it was pretty fascinating stuff. But by the end, I was ready for a change, and so this was around 2005 or so. And at that time, computational biology was a very, very new thing that was beginning to take off, and it was pretty exciting. Just a little bit of history. The Human Genome Project had been completed in the year 2000. That was the announcement of the first reading of the human genetic code, the 3 billion chemical letters, A, C, G, and T, that make up our recipe, if you will, inside each of our cells.
The recipe, I love it.
Yeah. So this was a big, new, exciting thing, and it looked pretty cool to me. And one thing about computational linguistics is I have found it interesting, but also kind of frustrating at times, because I was coming to it from a mathematical perspective where things are, tend to be pretty cut and dried. And, language is naturally squishy. We humans are not logical creatures always, and our language reflects that. So I thought to myself, this new computational biology stuff, it is digital. It's a sequence of A's, C's, G's, and T's. This is more kind of something I can get my teeth into, which was partly right and partly wrong. There's, fascinating mathematical science to be done here. But once you get into anything related to biology and living things, it does get squishy sooner or later. So, I have not gone away from squishiness and uncertainty. I've just kind of learned to like it better.
So when you say squishy, you just mean like not necessarily there's a cut or dry answer. Things are undefined. Things can change from day to day, and not necessarily logical.
Yeah, that's exactly right. If you have like a typical mathematical or computational problem, it's very precisely specified what it is. if you look inside a living cell, often we don't even know what questions to ask because we don't understand exactly what's going on inside our cells still after, however many years of investigating it.
Oh yeah, that's a whole thing. Hey, we teach these things to kids in high school and probably even in university, and at the molecular level, it's almost like magic.
Yeah, that's so. I mean, we are making progress slowly, but there's
true,
still to be learned. So anyway, having made this decision to get into computational biology, so it's a little unorthodox, but I decided to do a master's degree after my PhD, just as a quick way of getting trained up in the subject. So I went away and did that for a year. Half of that was at the University of Leeds in the north of England, and half of it was a placement at the European Bioinformatics Institute in Cambridge. And after doing that, that was great, and I wanted to stay in the field. So I needed a job and looked around at various academic jobs. But I ended up going with a startup company, which was a company called Solexa, which not many people have heard about, because a year or so after I joined them, they were absorbed by a much larger company called Illumina, which is still in business. So what Solexa were doing were developing new forms of sequencing technology. So the original Human Genome Project was done using a method using Sanger sequencing, which is very accurate, but it's quite slow and expensive. So at this time, sort of around 2006 or so, probably less than 100 people in the world had their genomes sequenced, and it was really expensive, tens of millions of dollars each time. So Solexa was working on a technology. It was spun out of the chemistry department at Cambridge University, and they were working on a technology to try and make this very much faster and cheaper. And to cut a long story short, they succeeded. We succeeded. I played a small part of that. So 10 years or so later, Illumina reached its goal of the $1,000 genome. So we'd gone from tens of millions of dollars to 1,000.
Whoa, that's an order of magnitude. Wow.
I know. It is just really a transformative thing, and the effects of that are just, still reverberating all around the science of biology. It's changing really quickly right now.
Mm-hmm.
So that was great. After about 5 years of doing this, I was again ready to do something else. So I moved to the Wellcome Trust Sanger Institute, which was still in Cambridge. And that's the place where the original Human Genome Project was done. And nowadays it's doing, pretty much any kind of human genome research you can imagine. They're working on it. So they're doing things on malaria, they're doing things on human genetics, things on cancer, all kinds of stuff. Mm-hmm. Tuberculosis. Right now, they've been heavily involved in the fight against COVID-19. So, a whole broad range of stuff. And so my time at Illumina and later at the Sanger Institute, I was mostly working on workflows and infrastructure to manage all this big data that genome sequencing is generating, because it's great that it's so fast and cheap, but it is producing huge volumes of data, which is a big challenge.
That's always the thing, hey?
Yeah, absolutely. I mean, so the Sanger Institute right now has 64 petabytes of data storage. So that's 64,000 terabytes. Just for comparison, Spotify a few years ago had 42 petabytes to handle all the music in the world and all their, couple of billion users.
That is a cool analogy. That is a well done. I love that. That gave me goosebumps.
Yeah, exactly. It does to me too when I stop and think about it. So this has been my bread and butter for the last, 15 years or so at this point. It started off, so I was hired on at Solexa as just a kind of general programmer and scientist. It was a startup. There was a wide range of things to do. And they thought I would be working more closely with the chemistry people to try and improve their technology and provide, data analysis input. And they thought it would be a temporary project, just write a few scripts to get the data analysis automated, and I'd be all done in 6 months. And, 15 years later, I'm still working on it to some extent. So, yeah, life takes us in directions we don't expect. But anyway, so after 6 years or so at the Sanger Institute, so I wanted to relocate back to Canada, partly for family reasons, because I have a young son and I wanted him to be closer to his grandparents. My wife's from the United States on the East Coast, so Toronto was kind of a happy medium between the two places. And it so happened I'd heard about this very good Cancer Research Institute in Toronto, which was applying all this genomic science to the study of cancer. So I talked to them, and they took me on, and that was about 3.5 years ago. It was in 2018, and here I am still. So recently I have changed direction slightly. I'm still involved a bit in the pipelines and workflows and data management, but I'm starting to get back more into the scientific side of things. So the team I work with right now is involved in producing clinical reports. So the idea is to sequence the tumor and normal genomes from a cancer patient. So you take some of the cancer cells, read their genome, take some normal cells, read their genome, and you compare the two, and you try and work out what mutations are driving the cancer. And hopefully this will give you information on how best to fight it. So that's what we're bringing forward right now, and we're trying to make it not just a research thing that is done in an academic university research sense, but something that becomes more and more widespread in the clinic. So we want, we're hoping 5-10 years from now, this can be a routine thing that cancer patients get.
Oh, cool. Wow. I love it. Well, what a cool way to wrap, you done. I'm kind of stuttering because I'm just, I'm a little super impressed here. So, do you have from your time in all of these different places, do you have like something that has stuck with you as like a cool story or something interesting you could share?
Yeah, certainly. So I've got something from the Sanger Institute during my time there. So this happened in 2015. So the campus where they are, it's about 10 miles or so outside of Cambridge. It's in a pretty rural area. But, it's nice, pleasant land. There's lots of nice trees and forests. It's next to a river. So, people have lived there for a long, long time. It's a good place to live. And by a long time, I mean, thousands of years. Especially when they do building work. So this is not so much a concern in North America, but anywhere in Europe or the UK, if you're doing any kind of building work or excavation or making a new building, then you have to have an archaeological survey just in case you're digging up some kind of remains from prehistoric times. So this is exactly what they did, and they found some skeletons.
Oh, wow.
On the campus. And so they dated them. And it turned out they were from between about 100 BCE to 700 CE. So, between about 1300 to 2100 years ago. So the most recent of these were 300 years before the current British royal family moved onto the throne. So, they're pretty old. And so it so happened we had lots of experts on DNA on site.
Oh, that was lucky.
Yeah, I know. So an interesting thing you can do is read the DNA from ancient samples like this. And it's quite challenging because DNA deteriorates over time. Unfortunately, the Jurassic Park scenario where we cloned some dinosaurs, or maybe fortunately, given how the movies turned out. But either way, it's not going to happen because DNA just falls apart long before then. We can't read it if it's more than about 1 million years old. But these skeletons were, well within the time frame we can work with, so we read their genomes. I say we, the lead was taken by specialists in this, but I was, writing some of the software that helped analyze the data. And they had a look at them, and they compared them to modern populations, and they found out some interesting things. So for one thing, about 38% of the genome in these skeletons was closely connected to people who lived in that part of the east of England today, which is kind of impressively high because it's been, up to 2,000 years. There's been a lot of conquest has come and gone, and populations have moved around, but still people have stayed put to a large degree. Families have. So, about 38% of the genome from these ancient skeletons had close relatives in people who are living around Cambridge today. Also interesting is, so they were closely related as well to populations in Denmark and the Netherlands, who are on the other side of the North Sea in mainland Europe. And in fact, they were more closely related to people in Denmark than they were to people in the southwest of England. It's about 300 miles away, but thousands of years ago, that was a long and difficult journey. Whereas, people were going back and forth across the ocean. So, in boats. So they were more closely related to Denmark, these ancient skeletons, than they were to the southwest of England, which I find fascinating because it's easy to think, especially of a long-established country like England, that, it's a kind of unified population and all the English people are more closely related to each other than they are to outsiders. But this isn't true at all. They have family ties, closer family ties to people in Denmark or the Netherlands than they do to some other people in England. So, this is science telling us we are all one human family, and our ancestry is a lot more complicated than you would think just by looking at a map.
And it was a heck of a thing to go on a 300-mile walk.
Exactly, yeah. 300 miles past wild animals and possibly hostile rival tribes and all this stuff. Yeah, that was a big
exactly.
deal in those days.
Yeah, that's a long ways to go. Even this is not probably within a realm of your job description. Would people back then have horses? Like, were horses domesticated in around Europe at that time? I'm just trying to think. I think they would have.
Certainly, like the Romans and people like that had domesticated horses. The sort of Iron Age, the more recent skeletons from about 700 CE or so, yes, they would have had horses. The earlier pre-Roman ones, it's hard to tell. I don't know what the archaeological consensus is.
I'm sorry to put you on the spot like that. It's just that would make it even more. Yeah. That would make it even more tough to even do anything way back then if you didn't have a horse.
Yeah, now I think of it because I think when the Romans arrived and tried to conquer Britain, there were people fighting them on chariots. I've partially got that from Hollywood, but I think maybe they did have horses at the time. But even with a horse, it's a hard journey. You don't have GPS or anything.
No GPS, yeah. Turn right at this hut. Watch out for the, unfriendly tribe that will stab you. Yeah.
yeah, exactly.
That is a cool story. Wow. Did that make media at the time? Like was the No, I was wondering, it's a big story.
Yeah, if you Google for it, you'll turn stuff up. There were news items on like the BBC and in the papers. Cool. They also made a little museum on site so you can go and see these skeletons and some of the tools and so on they dug up. Yeah.
Cool. Mm-hmm. Well, that's an interesting story. Thanks for sharing it.
Okay.
So you're now at the Ontario Institute for Cancer Research. You mentioned a little bit about your job description there. Could you go into just a little bit more detail for everybody, since this is like what you're currently doing?
Yeah, absolutely. So cancer is really a disease of the genome, of our genetic code. So it happens when things go wrong because, we're made up of trillions upon trillions of cells. They have to reproduce themselves in order for our body to function. Sometimes that goes wrong and you get mutations, and usually the mutations are harmless. Sometimes they're very bad for the cell and the cell just dies. But sometimes they cause the cell to continue reproducing itself and grow out of control, and that's where cancer comes from. And usually it doesn't happen from just one mutation. You have what are called driver mutations, and the first one will make the cells a little more inclined towards becoming cancerous. And your precancerous cells, maybe nothing happens, maybe they experience some more mutations, and a little while down the line, then they become full-blown cancer. So, if somebody has cancer, then it means there's a population of cells in their body which have a different genetic code and are replicating themselves differently and growing out of control. And this is bad because they're taking resources away from the rest of the body and, harming other cells and things like that. So what we want to do is work out what is making any particular cancer tick, because there are lots and lots of ways that cells can go wrong and start behaving in a cancerous way. Before genomics came along, you just had to kind of look at it through a microscope and try and, work out what it was doing from the shape of the tumor growth or something like that. But now we can, because of this amazing, fast, cheap DNA sequencing we have today, we can read the entire genetic code of the tumor. We can also read the RNA, the proteins that it's expressing. And we can compare that with the same information from healthy cells. So we can say, okay, here is how this cancer cell has changed. Now, the thing about cancer cells is once they start going wrong, they tend to go very, very wrong. So by the time we come to, put somebody in the hospital and treat them for cancer, usually the cancer genome, it doesn't have just 4 or 5 mutations, it has thousands of them. And not just little mutations, but like whole sections of the genome can be rearranged or missing or amplified or deleted or reversed in direction. All kinds of strange things can happen. So our job first is to untangle this. So we get the genetic code off of a sequencing machine, and it's effectively just a list of A, C's, G's, and T's. So we need to put that together. We need to work out where the cancer and the normal genomes differ from each other. And we need to compare to kind of known databases of mutations and work out which ones are important, which ones are driving the cancer. And, we might just know this by correlation, so the mutation has been seen in lots of different cancers, or we might have an idea of the mechanism behind it. So this mutation changes a certain protein, which means the cell is no longer responsive to a particular hormone within the body, so that means it doesn't stop growing when it's meant to, and it keeps growing. This is the kind of thing that happens. And ideally, if we know the mechanism at work, we can recommend a drug. So we can say, okay, this tumor is growing out of control because of this hormone it's coming into contact with within the body, this biochemical signal. If we can give it a drug that blocks that signal, then the cancer will stop growing. So, so we do all of these things, and we have lots of different kinds of variant in the genome that we identify. As I say, there are simple ones where maybe there's just a single letter swapped from A to C or A to G. But there can be much bigger ones, as I say, where sections of the genome are deleted and rearranged. So what we do is, in my team, is we sit at the end of this process and we gather together all the information that our automated pipelines have produced and produce a fairly short 2 or 3 page document that summarizes all of it. And we can then give this to the doctor who's treating the patient, and the document will say, well, here are the variants we've identified. Here are some known drugs which may be effective on this patient, and the doctor can take it from there and try and treat the cancer.
So it's targeted treatment instead of guesswork or...
Absolutely, yes. Personalized medicine is the goal that we're striving towards here.
Wow, cool.
Yeah.
I totally get it now. Thank you for explaining that.
Oh, you're welcome. So yes, a lot of this process is automated, but there's still kind of a lot of room for human effort and judgment. So we write like a brief kind of couple of paragraph summary of what's going on. And at the moment that is handwritten. I'd love to go back to my computational linguistics roots and have a computer which will make it for me automatically, but that's going to take a little bit of effort. We're not there yet.
Gotcha. All right. Well, that was fascinating. Thanks for talking about what you do in, this new position that you're in. Mm-hmm. I'd imagine it's kind of exciting because this could potentially, or does, drastically change people's lives when it gets right.
Oh, it does. Yeah. I mean, it's a very satisfying thing because, if I'm producing a clinical report, it's all anonymized for reasons of patient confidentiality.
Oh, yeah. Yeah,
so,
exactly.
I don't know their name or their date of birth or that much about them, but I know it's a real person, and I know I'm, trying to help them with this, this terrible disease. And, this is all in a fairly early research stage, and people who are doing this are enrolled as part of a clinical trial to test out, new medical approaches. And, cancer is a very terrible thing, and some of them might not make it, even if we do make this report for them. But we can learn from them. We can learn from the experience we've had reporting for them and try and make it better. So, even if it doesn't benefit someone today, it might, 5, 10, 20 years from now.
Very profound. So all of these jobs you've had are with computers. Yeah. And like I have a couple questions about the future of computers and computing power. Where do you feel increase in computing power, and as computers get better and better, where do you think is that going to take us? And then the flip side is like, do you foresee some, a dark side to the increased computing power that we're going to be having throughout society?
Yeah, certainly. So,
sorry to put you on the spot, but I always love asking people that question.
Thing first and trying to look into the future. Hey, that's great. I mean, I have a PhD in artificial intelligence. If you can't ask me, you can't ask anybody. So yeah, I think, to a large extent, the revolution is already here. I mean, it's easy to overlook that computers have transformed our lives in ways we couldn't have imagined, 20 years ago, let alone 50 years ago. And to a large extent, it's been kind of seamless. We don't have like robot butlers walking around our houses, but it would be nice, but we don't have those. What we do have is computers, seamlessly becoming part of our lives and making a lot of everyday things easier. And I think that's going to continue, and it's going to get smarter. We won't. The best things will probably be the things where we don't even notice they're there. They just make things, simpler and easier on an everyday level. So, for instance, there's been a lot of hype around self-driving cars, but it turns out that's an extremely difficult problem. It may be a long time, if ever, before we get to a truly self-driving car. But if you buy a new car today, it will have lots and lots of sensors and gadgets that anticipate what you're doing and, try and make you safer and warn you if you're doing something unsafe. And I think that's going to become something more and more common that we take for granted. Or to give another example, so my son is 6 years old and he has a mild learning disability. So he has trouble kind of reading text and writing. When I was his age, I was lucky I didn't have that. But if I had, then it would have just been, well, okay, you just have to kind of struggle through and we'll try and help you, but there's only so much we can do. But right now he can use text to speech to write things for class, and that's just seamlessly part of Google Docs. It's a thing that's easy and available for free. And I think things of that nature will become smarter and better and more useful to us. And looking forward to something that is not here yet, but hopefully will be, within a generation or so, maybe less. So I've talked about applying drugs to cancer. Where we get drugs from is still kind of old school. We're still reliant to a large extent on plant compounds, fungi, things like that. What we would ideally like to do as part of this smart medicine approach is to be able to design drugs from scratch. Assemble a molecule up from its component atoms and design it specifically to target some other molecule in our bodies or in like a bacteria or a virus that's of interest to us.
Yeah.
And, we are beginning to get there with things like the RNA viruses for COVID-19, of course. but there is a lot more potential for that, especially in cancer research.
Oh, I heard about
So
I heard about
there
this.
was a
Yeah.
very exciting
Go ahead.
result from a thing called AlphaFold, which was announced last year. Yeah, exactly. This is really cool stuff. So one of the big problems in computational biology is, as I said, we can read the recipe, we can read, the A's, C's, G's, and T's. It's not so much a recipe, though, as an ingredients list. It doesn't tell you how to get from this, linear sequence to a three-dimensional protein molecule. That's dependent on, some quite complicated stuff with how the DNA is transcribed in the body and how the amino acids that make up the protein kind of electrochemically interact with each other and what causes it to fold into a certain three-dimensional shape. The amazing thing is it does this very complicated folding very reliably, billions of times constantly in our bodies. So we would like to be able to understand how it works and predict it in a computer. And if we can do that, then we can evaluate new drugs and design new drugs to target particular proteins. So, if you have a cancer cell that's producing a particular kind of abnormal protein, then maybe you can make a drug that will destroy cells which have that protein and only those cells. That would be a great thing to have. So this is a thing we are slowly working towards in modern day biology. I talk about computational biology, but really it's just biology. More and more computers are becoming integrated.
It's exciting. I'm excited for that. That's very cool.
Yeah, indeed. But anyway, to take the other part of your question about the dark side, again, I don't wish to sound alarmist, but to a large extent, the dark side is already here. So the threat to us is not, intelligent robots that are going to produce some Skynet scenario and declare war on the human race.
So we don't need to start, cloning Arnold Schwarzenegger to help us in the future.
Which is probably a good thing. I don't think that would end well. So computers are just a tool, and they will be just a tool for the foreseeable future. They're a very powerful tool. And the interesting thing is what kind of use we put them to. And we have to understand their limitations as well. So on the one hand, you have people who are deliberately doing, to put it simplistically, bad things with technology. There are parts of the world where it's used for mass surveillance and things like that to try and keep people under control and make sure nobody steps out of line. And, that is not a good thing. And as I say, computers are becoming more and more clever all the time. And these kinds of techniques are going to become more powerful. So that's a danger we have to be concerned with. And, that's, again, it's not inherent to the technology, but it's how governments are choosing to apply it. And another risk is not so much, the big brother, the big scary government looming over us, but more a kind of bottom-up thing where people are being careless and not bothering to think about the implications of what they're doing. And again, this is not a scenario where you unleash killer robots on the world necessarily, but, more mundane things. So job screening tools are becoming a thing now where you will give an interview on video, but it's not watched by a human being, it's evaluated by a computer. And, this is a very cool sci-fi sounding idea, but my understanding is the tools are just not ready yet. They are not very accurate. They are very biased. They will tend to lead you to hire people much like the ones who are already working for you, which is bad news if you don't come from a typical background. Not to be too fine a point on it, if you're a white male and went to a big name university, these tools will favor you because that is the kind of data they've been trained on. And so, this is a thing that needs to be done very, very carefully. And just to take an even more mundane example, someone came up with a hand dryer, that you put in a public bathroom. So instead of having to touch a button to make it work, you wave your hand under a sensor, and they thought they had a really good new sensor that would do this. The trouble was, it had, again, only been trained on people with light-colored skin. It would not work for dark-skinned people. But they didn't realize this until it had gone to market and already been installed in a bunch of places.
Oh, my goodness.
So, prejudice is a thing, sadly, that can go hand in hand with technology, but ultimately the responsibility lies with us, not the technology, to try and deal with it. And another aspect of the dark side is just wasted effort. I've talked about self-driving cars, and there's been a colossal amount of money dropped on these things by Uber and other companies. And, arguably past the point where it was clear that it was not going to produce a very good return in the foreseeable future. Amazon spent a fortune on a delivery system using aerial drones, which again sounds like a really cool and exciting sci-fi idea. The only trouble is it didn't work. And, it's usually possible to predict not always, but usually you can have an idea when something isn't working, especially once you've done a pilot study and tried to do it a little bit. Because technology isn't magic. It won't produce the Arnold Schwarzenegger Terminator again in the foreseeable future. It does not repeal the laws of arithmetic. 1 + 1 still equals 2. And self-driving cars are a terrifically cool idea, but, it doesn't change the physics and the numbers of how many cars you can fit into a certain length of highway or a certain length of city street. So if traffic jams are a problem in downtown Toronto, which they are, self-driving cars are not really going to help us much. We need to consider other solutions.
Great. I love the future. The future is very exciting, and I do appreciate your insight into how the stuff that we take for granted is the good side of computers, and some of the things we need to think more about, the bad sides, are already here. Can I ask one follow-up question? Since you're a computer person, do you think they'll ever figure out self-driving cars, or do you think that's just it's just too complicated for what we have right now?
Well, I don't want to say never, but I think it would take a huge leap in computing hardware to make it possible.
Right.
Because this is another kind of insight from biology. The human brain can drive a car, but the human brain is tremendously complicated, a lot more than we've given it credit for. And our current computer technologies are very impressive, but they just cannot function with the same kind of bandwidth and process as much data as quickly as a human brain does.
Right. A self-driving car can go around a track that has no other cars on it, and it doesn't really have to make split-second judgments. But also I read that sometimes the self-driving car has been trained to see certain things and then crashes. It sees a semi-truck sideways as sky through no fault of its own. It's just little mistakes like that, but that's a disaster if you're the person inside it.
Yeah, very much so. I mean, this is one of the dangers of our current AI technology. At the same time, it's too smart and not smart enough. Because it's not smart enough to do everything human beings can do. But at the same time, it is smart enough that we can't always understand why it does what it does. It's effectively a black box. We've trained it to do certain things, and it does them in test conditions. But if we put it out in the real world, it may do something completely unexpected, and we won't know why, and we won't be able to predict why.
You just have to sit there and scratch your head. Why did you do that?
Yeah, exactly. Look at the wreckage and go, oh, well, back to the drawing board.
Oh, yeah.
But, for a self-driving car, obviously, that's, not a great position to be in.
No, very different than some of the more mundane but still very important things that AI can sometimes take people out of the running for jobs, for sure. Yeah,
no, it's true. And, you talked about self-driving cars on tracks, and, the successful road tests have been in places like Arizona where, the roads are pretty straight. There's not that much population and everything is pretty predictable. There aren't so many pedestrians because it's too hot out, But if you put them on a street in downtown Edmonton or Toronto, or let alone somewhere like England where the roads are really bendy and there's, lots of narrow streets and pedestrians and bicycles, they just can't cope, and it'll be a long time before they can.
Gotcha. All right. Well, thanks for giving us a little chat about the future. Let's switch things up a bit. We have a couple standard questions that we ask on the podcast, and one of them, well, I think they're all fun. The first one is a pet story. Would you have a pet story from your life you could share with us, since we mix science and pets on the podcast?
Yes, indeed. So I love dogs, but I've never had a dog of my own. I've had cats for about 10 years now. So this is one of our previous cats who was with us when we lived in England, and her name was Belle. And she was very keen on hunting things. So she had a cat flap to go out into the backyard, and she would go and capture things and bring them back in for our excitement. So one night I was sitting next to a window reading, and I had a lamp on that was right next to the window as well. And this lamp had attracted a whole lot of bugs. And, summer evening, there's moths and what have you flying around. And I saw Belle outside jumping around like a mad thing. And I thought, oh, she's trying to catch bugs again. Okay, fine. And after a while, I put down my book and I went away upstairs to go do something else. And so I'm there minding my own business, and from downstairs I hear my wife yell, "Iain, come quick!" So I run downstairs, and Belle has brought in a bat.
Oh no!
So she wasn't chasing the bugs at all. She was chasing the bats that were chasing the bugs. It was the food chain in action here. So our cat is very excited and pleased with herself, and there's a bat flapping around the living room. So first we took hold of Belle, who was very disappointed, and put her in another room so she couldn't interfere with things. And the bat was very disoriented and squeaking and flapping around. And eventually I managed to catch it in a kind of shopping bag. And at that point, it just kind of stayed still. I think its instinct made it to play dead or something. And it didn't seem to have been hurt seriously. Thankfully, it maybe had a couple of little kind of injuries from being dragged inside from my cat, but it looked basically okay. So I kind of took it outside into the garden, well away from the cat flap, and set it free, and it sort of flied off. And then I went inside and closed the cat flap so that Belle couldn't go out and hunt it again. So, it's very exciting having cats who are allowed to go outside and hunt for things. I now live in a condo building in Toronto with no outdoor access for my cat, which is, I think, for the best. It's a quieter life that way.
Yeah, it's probably a safer life for your cat too.
Yeah, that too. Cats can get in a lot of trouble outside, and obviously it's dangerous to the local bird and rodent and bat population as well. So I've come around to the idea that cats are best off inside.
That just shows the statistics that cats are just such incredible hunters.
They really are. I mean, catching a bat on the wing is pretty impressive, I have to say.
I have to say, too. And brave, too. That's kind of an odd thing that's definitely different than its normal thing it might be trying to hunt. So
Yeah.
No bat bites, though. We didn't get some kind of cat vampire.
No, she didn't show any vampire signs. And thankfully this was England, where rabies isn't really a thing, so we didn't have to worry about that. Yeah.
Well, thanks for sharing your pet story. That was awesome. Mm-hmm. The other question we ask is our guest to share, if you can, is a super fact. It's something that that when you tell people, it kind of blows their mind a bit. Do you have a super fact you could share with us?
Yes, I do. So this touches on what I've said already. So the super fact is that cancer is a part of us. And so I'll explain what I mean by that. As I said, cancer is just our own cells reproducing out of control. Coronavirus is a thing that's external to the body. It comes in, it makes you sick. Cancer is something that arises from inside you. And as I've said, cells have to reproduce themselves, just as part of being a living organism. To replace cells that have been damaged or worn out, your body needs to make new ones, and it does. And it's amazingly accurate at this. There's 3 billion letters in the human genetic code. There are upwards of 3 trillion cells in the body, at a rough estimate. We don't know exactly how many. And most of the time it goes along just fine. But as I've said, every so often, a cancer cell will develop. Not right away. You get, some precursor mutations. But after 4 or 5 cancer driver mutations have occurred, then you get cancer. And these mutations are just, mutation is a scary word. It makes you think of, old movies of people, being transformed by green slime into horrible monsters.
Or
but
turtles. Or Ninja Turtles.
Ninja Turtles. Yeah, exactly. Yeah, case in point. So yeah, green ooze doesn't have to be involved. It just, it is part of life. Your cells replicate themselves with amazing accuracy, but just every so often they get it wrong. And usually that's harmless, but sometimes it isn't. And these cancer mutations, they can occur in anyone at any age. They become more likely as you get older, but that's just because you have more time. It's a random process. If you sit there flipping a coin, then you're more likely to see ahead if you flip it 10 times than if you flip it just once.
Mm-hmm.
So, and this ties into, there's a belief that you can protect yourself from cancer by eating the right diet, doing the right exercise, things like that. And it's just not true. These are good things to do. They will help you, all else being equal, live a long and healthy life. But in terms of cancer, they just move the odds a little bit. That's all. And you can still be unlucky. So cancer is not like chess. It's more like poker. If I play the best chess player in the world, I will lose. I will lose every time. There's really not much question there. If I play the best poker player in the world, I've got a significant chance of winning. Not huge, and over time he'll be able to beat me if we play a lot. But, cancer only has to get lucky once. And sometimes, metaphorically speaking, cancer draws the royal flush. And it doesn't matter if you've been eating healthy and exercising and all these things, you can still get cancer. So with what I do in cancer research, much as we'd like to, we can't change the rules. We're stuck with the, a billion years worth of biological inheritance. What we are doing is trying to cheat and, take our opponent at poker and, switch out their cards or switch in better cards for us. So cancer research is like cheating at poker. That's what we're aiming for here.
That is an astoundingly good analogy, Iain.
Thank you.
Well done. I'm just smiling from ear to ear. I know cancer is a very serious subject, but I'm big on the whole analogy thing, and that's just so. Can I steal that in the future to talk about?
Yes, by all means.
Okay, all right, thank you.
Yes, if you're
it's
talking
so
to your class
good.
or whatever.
It's so good.
Thank you. Yes,
that is a super fact, and that is a super explanation for what you do.
Well, thank you very much. Yeah, and I'd like to stay positive because cancer is a bad thing and a scary thing. I've had family who have got it. Pretty much everyone has. But, it's important to stay positive and understand that we are making progress every day and trying to make things better. And, the flip side of the fact that anyone can get cancer is, progress in cancer is important for everyone. Progress in cancer research.
Yep. Yeah, what affects us all means we must all work to affect it.
Mm-hmm.
Perfect. Well, that is a great super fact. Thank you for sharing that with us. I'm sure some people are going to be like taking that little snippet of you and using your explanation also in their own lives. So I think that's going to affect people's understanding of the difference between cancer treatment and cancer. So that's great.
Oh, good. I hope so. I'm glad if I can help.
Yeah. The last section of the podcast is one where we get to know a little bit more about our guests outside of their career. It's the important to you section. And guests talk about hobbies, sports, causes. You wanted to talk about sports and rugby and how maybe thinking for you have changed about that.
Yeah, absolutely. So, so I came to rugby kind of late. As I said, I went to school in the UK, so I was subjected to rugby in gym class at school, and I did not like it one little bit. So, as you've gathered, I'm a nerd, not to put too fine a point on it. I like reading and learning. And, quite early on in my life, I was on, the nerd side of the nerd jock divide that we all know from movies and TV. So just as a cultural thing, I was opposed to most forms of physical activity. And rugby was particularly bad because, it's a contact sport. I was getting pushed around. And also, I didn't understand the rules at all because I'd quite recently moved from Canada. So I only had the vaguest idea of what I was meant to be doing. sometime after that, I went away to university, and I kind of found my niche for physical activity. And I found out that I can actually be pretty good at some forms of it. So I did martial arts for a while. I don't do it anymore because I'm not as young as I used to be, and it's pretty intense. But for a while, I was doing, martial arts like 3-4 times a week and getting pretty good at it. And just to have like a supportive atmosphere and something to build up my confidence in it was really helpful, which unfortunately at that time, school gym classes weren't providing very well. So I did that. These days I do lots of hiking, I do canoeing, I do cycling, and that's all great because I enjoy my work, sitting in front of a computer screen mostly, and I enjoy sitting back with a movie as much as anyone. But it is good to get outside and move your body, and your brain feels better from it as well. But getting on to rugby, so my wife is from the United States, and we got married in 2008, and she moved to the UK from the USA. We'd actually met in Scotland while I was doing my PhD, and we did the long distance thing for a while and eventually decided to settle in the UK. And she was a big fan of American football, and this was 2008 or so. They didn't have the streaming services they have now. It was quite hard to get broadcasts of it, certainly if you want them for a specific team. It didn't work. So as a substitute, and I've talked about time differences as well. The time difference is pretty brutal if it's, minimum 5 hours. So she, as a substitute, had a look at rugby, which, is very different from American football, but, it's a contact sport with an oval ball that you're trying to kick or carry across a goal line. There is some fundamental similarities there. And so she started watching it, and I started watching it, and we got to really like it and start following it. And in 2015, they had the Rugby World Cup hosted in England, and we went to a bunch of the games, and I went and saw Canada lose to Italy, which wasn't the ideal outcome, but on the whole it was really great fun. And what I came to appreciate about rugby, and so just a little word on the difference between rugby and football, because to a lot of people in North America rugby is just a word. So in football it's very stop-start, so the game is broken up into plays. The quarterback, throws their hands off the ball to someone who tries to carry it forward. That person scores or gets tackled, and then they reset everything and start again. Rugby is a lot more fluid. There's a lot more passing the ball between players. The ball can turn over between teams without a stoppage of play. So it can be really exciting. Things can transform very quickly. And so those are rugby specific things. And also, so there's an old joke that, so soccer is a non-contact sport. It's very nice. You're not supposed to bang into anyone or crash into them. However, this is not always borne out on the soccer field. So there is an old joke that soccer is a game for gentlemen played by brutes, and rugby is a game for brutes played by gentlemen. Because in rugby, there has to be a culture of sportsmanship and taking care of each other, even on the opposing team, because it is a very, very rough contact sport. And if you play it in an unsafe way, people will get hurt. And they want to minimize that, and they penalize it very heavily. But the penalties are not just being sent off and told you can't play for the rest of the game. It's, the disapproval of your team. So that's a thing in rugby that I've grown to really appreciate. And other things that, rugby has but are common to all sports. So, again, as a young kid, on the nerd side of the divide, I had the impression that sports were just for, large, stupid people, to put it bluntly. But this is not so, having gotten into sports properly and watched them over time, there's a lot of thinking involved. There's psychology, there's teamwork, there's tactics, and, you need to be pretty smart to play a team sport successfully, especially at kind of an elite level. So, this is something I've grown to appreciate, and, maybe other people should try and appreciate more too. So just to give an example, so a week or two ago, the quarterback of the Green Bay Packers of the NFL, Aaron
Oh
Rodgers,
boy.
made very, very foolish remarks about vaccines and how he was anti-COVID vaccine. And I'm not going to get into the details of those, except to say that I disagree with them very strongly. But people were saying on Twitter, it only goes to show he's an athlete. He's been hit in the head too many times. You know, you should not follow athletes' advice on anything or have them as role models. And this, I think, is really missing the boat, because athletes, as I say, have to be very smart people, very disciplined people. And, you know, it is fine to admire someone for the dedication and the teamwork that they bring to sports. And the real lesson of having heroes in sports or science or any other field of endeavor is you should not put anyone on too high a pedestal, because everyone is human and occasionally anyone could do something terrible.
Well, that gives me a lot to think about. I agree with you on sports. I love sports. I love the idea of sports. When I have time, I like watching sports. I love listening to the occasion athlete make like such a wise comment or something so profound. Charles Barkley comes to mind. Occasionally, man, does he just have a couple gems that he says about things about life, not even in the NBA, that I enjoy. Well, Doctor, it's been my pleasure to talk to you today. This has been an absolutely amazing interview. We've gone all over the place, which I love. I hope people understand that like this podcast had one direction, and we went from your background to digging up skeletons to talking about the futures of computing, an amazing analogy about cancer, and we ended with rugby. Like, this has been an amazing talk. So just from me to you, thanks for talking to us on the podcast about what you study and the things that you've experienced in your life.
Well, you're welcome. My pleasure.
Where can people follow you on social media? Do you have a social media account, or is there any organization you'd like people to look into?
Okay, well, I am on Twitter as Iain Bancarz. My handle is the same as my name. And you are welcome to follow me. I tweet largely silliness about sports and occasionally serious things about science and technology, not necessarily related to my job.
That's okay. We need some of that in our lives. Totally get it. Yeah.
Mm-hmm.
All right. Well, we'll make sure that handle is in the show notes to the episode.
Well, thank you. Thanks for having me, and give my best to Bunsen and Beaker.
Okay, it's time for story time with me, Adam. If you don't know what story time is when we talk about stories that have happened within the past 1 or 2 weeks. Dad, do you have a story?
It does involve the dogs, because the dogs have brought us a lot of ability to have a message on social media of science, empathy, and cuteness. And we've started these Twitter spaces. They run twice a week. And the community that has grown around us running these two spaces has been really cool and really rewarding. The one space is just called Pet Chat. And we tell stories about Bunsen and Beaker. Similar, it's longer than this section you're listening to now. And Chris and I riff back and forth, but then we invite people from the public to come up and share their pet stories. And we have a lot of feedback that this is a lot of people, their favorite part is listening to Adam run the show and us talk about Bunsen and Beaker. And they really like this part of the podcast. So we made an entire hour show about it. And it's been really rewarding to see it grow. And we have people that come back week after week and are comfortable to share their stories. So, well, this is it a story about Bunsen and Beaker? I think it's a story about what Bunsen and Beaker has brought to social media, and that's a community of wholesome, caring people. And I think that's kind of cool. That's my story.
All right. Well, I have a story.
Look at Bunsen's face.
Yeah, look at his face. He's so smiley. So, Bunsen has been a little cute boy. I've been getting up on the couch with him, and he will jump up with me now. He will now jump up and cuddle with me all the time. And I don't know why it's recently that he's been doing this. He's been doing it with Mom all the time. But just today, this morning, I came upstairs and I sat down on the couch because I woke up really early by accident. And both the dogs were there with me. Bunsen came and sat down, and then 2 minutes later, Beaker came and sat down. And then the same thing happened after school.
Becoming like a couch bear, hey?
Yeah, he's a little smiley couch bear. And Beaker's sad because we're giving Bunsen all the attention. But yeah, after school, they did the same thing. And I was laying down, and Beaker wanted up, so I had to move and stop laying down so that she could get up. But yeah, that's my story. Mom, do you have a story?
I sure do. Beaker is still in level 2, and she's had her second lesson tonight. Now, this is level 2 redo. So she has had all the skills taught to her before, but she's just improving so much. Tonight, she was so happy to be working and learning, and her brain is like a little computer. It's so cute how she figures things out. One of my favorite parts of tonight's lesson was pause up, because before she didn't do it. And now tonight she was just like, oh, I see a stool. Bloop. Pause up. She didn't even have to do like the preliminary work to get on it. It was amazing. And I attribute that to Bunsen. When he saw the stool, he was like, oh yeah, Kool-Aid man, jumped on it, and he was pause up boy. And I think he really helped her learn that skill. Right, buddy? Any more?
All right. Well, that's the end of story time. I can't wait to see you guys in the next episode of the podcast. Bye-bye.
Well, that's the end of another Science Podcast episode. Thanks so much for coming back week after week to listen to our show. Special thanks to Dr. Iain Bancarz, who talked to us all about crunching the numbers and cancer. Some really important messages there. We'd also like to take this time to thank our top-tier patrons on Patreon. Without their support, well, we wouldn't be able to do what we do. So take it away, Chris.
Chris Kelly, Samantha Dodd, Kimberly Bond, Nate Stephenson, Debbie Anderson, Courtney Proven, Renee Hardy, Mary Rater, Shelby Leggett, Mary Coos, Katya Lynch, Marianne McNally, Andrea Persons, Elizabeth Bourgeois, Karen Beth St. George, Bianca Hyde, Sandy Breimer, Tracy Halberg, Jenny Jaguar, Leela Perriello, Lynn Armstrong, Lisa Swartz, Catherine Jordan, Donna Craig, Lila Ashir, Jody Ogren, Liz Button, Kathy Zerker, and Ben Rathert.
For science, empathy, and cuteness.